All right. Is it time yet? Yes, it is. Cool. So separable or not? This first one, definitely separable. We can totally write the right-hand side. I should say, we can totally isolate dy dx, which all of these already have it isolated, and write the other side as a product of a function of x and a function of y. Bless you. So yeah, right, here's my, let's just do this instead here. Here's my f of x. Here's my g of y. So I could totally separate them. The answer here is definitely yes. We could bring the y stuff to the left and say I have 1 over y times y minus 2 equal to, sorry, times dy equal to x times dx. We have separated it. All the y's on the left, all the x's on the right. This next one is not. We cannot separate this differential equation. There's no way to get some stuff with y's times dy equal to some stuff with x's times dx. Just can't be done. Like there's nothing, I can't even really do anything, right? Like I could bring the dx over, dy equals 3x minus 2y. That's a problem. There's no way to get that y over there without trying to bring dx along with it. Or I guess you could add 2y to both sides first. 2y plus dy dx equals 3x. But don't fool yourself here. If you try multiplying everything by dx, you get 2y times dx plus dy equal to 3x times. That's a problem too. That's a big, I don't want dx's all over the place here. Can't be done. We'll talk about how we deal with this kind of problem today, actually. This third one can be separated. We could totally factor out an x squared from the right-hand side and say that we have dy dx equal to x squared times y minus 1, and then bring the y's to the left, so divide by y minus 1, bring the x's to the right, multiply both sides by dx. Cool. Let's talk about how, so here's what I'm going to say very generally. If someone asks you to solve a differential equation, you should expect for it either to be separable. I guess you could, I mean, you could either really just be like dy dx equals some stuff and then you just integrate it if it's just stuff with x's, or it's going to be separable, or it's going to be the other thing we're going to talk about today. But if something is solvable, right, if you can solve a differential equation, it either has to be separable or it has to be this other thing, which is a first order linear differential equation, which we'll talk about today. But let's talk about solving these two separable ones first, just because they're already there. We might as well do it. And then we'll come back to this one. And actually, let's do the third one first. So how would we solve 1 over y minus 1 times dy equal to x squared times dx? Well, of course, we would anti-differentiate both sides. I'm always looking for the final. There we go. There. Sorry, it's hiding from me. Fine, we'll just use that one. The integral of 1 over y minus 1 is the natural log of the absolute value of y minus 1. The integral of x squared is x cubed over 3 plus c. Let's give ourselves an initial condition as well. Why not? Let's say, let's say that y of 0 is equal to -4. Yeah, that should be fine. So is this my moment? This is not my moment. I do not want to plug in 0 for x and -4 for y and try and find c and then carry that through the other 2 or 3 steps I'm going to do to solve this differential equation. So let's wait a bit. Let's exponentiate both sides and let's just ignore the absolute values here. So we've got y minus 1 equal to e to the all this, which then becomes y minus 1 equal to e to the x cubed over 3 times e to the c. Let's rewrite that as y equal to 1 plus, let's call e to the c a, e to the x cubed over 3. Now is our moment. We have got the constant pretty much as isolated as it can be. Now we're going to plug in x equal to 0 and y equal to -4. So we're going to get -4 equal to 1 plus, maybe I should have left the 1 on the other side. Not that big a deal to bring it back over to the other side. A e to the 0th power. So -4 minus 1 is -5 equals a. So that means our solution, our particular solution, if you want to be particular about it, is y as a function of x is equal to 1 minus 5e to the x cubed over 3. And it is totally fine to ignore the absolute value, because basically solving for a here and getting to be positive if it needs to be positive, or negative if it needs to be negative, takes care of the fact that we had an absolute value there. So we don't need to worry about that. Not too terrible. Pretty standard. Let's look at the other one that was the other separable one. So let's say we have this other differential equation that we were looking to solve. We wanted to solve, where'd you go? 1 over y times y minus 2 dy equal to x times dx. The right-hand side looks fine here. The left-hand side looks like not fine. Looks like partial fractions. So on the left-hand side, we are going to have to do partial fractions. Okay. Usual partial fraction decomposition. Take your fraction, 1 over y times y minus 2. It's already factored for us. And we're going to write it as some constant divided by y plus some other constant divided by y minus 2. I would encourage everyone to think of the next step as just multiplying everything by the common denominator. So multiplying the whole equation by y times y minus 2. Multiply it there, I get 1. Multiply it there, the y's cancel. I get a times y minus 2. Multiply it here, the y minus 2 is canceled. You get b times y. This one you could do really easily the equating coefficients way. If you really wanted to, you could say if I multiply this out, I've got 1 equal to a times y minus 2a plus b times y, or if I combine my coefficients, I've got an a plus b times y minus 2a. So if you're doing this the equating coefficients way, which is not the way I would do it, but I'm going to show it just because I know teachers have talked about it. I would say here, oh, well, a plus b has to equal 0, because the amount of y on the left is 0 and the amount of y on the right has to be 0. And the constant term, 1 has to equal negative 2a. So great, that means a is going to equal negative 1/2. And then if a is negative 1/2, negative 1/2 plus b equals 0. So b has to equal positive 1/2. And while it's totally fine to do it this way, you really shouldn't do it this way. It's fine, like it's not bad here, but for things that are more complicated, it's much more work. So the way I would encourage everyone to really do these partial fractions problems is start by using your nice values of y, or whatever your variable is. I'm going to use y equal to 2. So that's going to make this part 0. And if y is 2, I have 1 equal to b times 2. So b is equal to 1/2. And then y equals 0 makes this term go away. So set y equal to 0. Still have 1 on the left. I have a times 0 minus 2. Oh, so 1 divided by negative 2. That's going to be a. Same values, either way you do it. I think doing it this way is usually nicer. The only thing I'll mention about this is if you have a repeated linear factor, like you have y minus 2 squared or x plus 1 to the third or something like that, then you will run out of nice values to use. And then you will have to implement some other method in addition, which we can talk about more if you want to, but that's not really the focus of what we're doing today. So we'll come back to that if needed. All right, so now on the left-hand side, we have the integral of negative 1/2 over y plus 1/2 over y minus 2. And that's equal to the integral of x, which is x squared over 2 plus c. All right, so we're going to integrate this. It's going to get a little bit messy here. We're going to get negative 1/2 natural log of the absolute value of y plus 1/2 natural log of the absolute value of y minus 2 equal to x squared over 2 plus c. Many of these, what do you call them? Differential equations problems say that you're supposed to solve for y as a function of x if possible. Sometimes it's not possible. Sometimes you get something like y plus cosine of y equal to x squared. You're like, I can't solve that for y. Can't be done. Here, it can be done. We can solve this for y. Let's see how. Because I think this does actually come up. So we should solve this for y at least once. So here's the process. Ooh, solving for y. So we got to put those natural logs together. So I would probably factor out the 1/2 and rewrite this left-hand side as 1/2 times. I'm going to write this one first. The natural log of the absolute value of y minus 2 minus the natural log of the absolute value of y equal to x squared over 2 plus c. Well, let's be smart. Let's multiply everything by 2. That seems like a smart thing to do that I wasn't thinking of doing until just now. We multiply everything by 2 and also combine this into the natural log of the absolute value of y minus 2 divided by y. Multiply the left-hand side by 2. Multiply the right-hand side by 2. 2 times x squared over 2 is x squared. And 2 times a constant is a constant. We're going to call it the same thing. I know nobody likes it, but everybody does it. So, yeah, that's what we do. And then we exponentiate both sides. Bless you. I'm going to get the e to the this equal to e to the that. So e to the natural log of some stuff is just the stuff. You get the absolute value of y minus 2 over y equal to e to the x squared times e to the c. And then we call that e to the c. For some reason, I don't know why, really honestly, people call it a instead of c again. We just do. Not everyone does. Some people just call it c. Either way is fine, whatever you want to call it. So I'm going to rewrite this as, I'm going to drop the absolute values and write this as y minus 2 over y equal to a times e to the x squared. And now we can solve for y. There's a number of ways to do this. How would I do it? How would I do it, really? I don't know how I would actually do it. Like, I don't know, like, if I was doing this, the best way to do it, there's like probably 3 different ways you can do it. One way is to flip both sides and say y over y might. No, that's not good, James. That's fine. Here's what I would do, really. I would multiply both sides by y. So y minus 2 equals a e to the x squared times y. Bring all the y's to one side. I would probably bring them to the left so that the 2 can be positive on the other side. So y minus a e to the x squared times y equals positive 2. Factor out the y. So we got 1 minus a e to the x squared equals 2. And then finally divide by that to get y equal to 2 over 1 minus a e to the x squared. That's your solution. That's your general solution, right? We didn't have an initial condition to solve for a for, so this is our general solution. You probably, you probably won't need to do this. But I definitely remember one quarter in 17B, there was a professor who was like super big on like having students do this stuff all the time. So felt like I should show it to you at least once. Oh yeah, he was asking some terrible questions. Just there was one guy who was just like really was hitting this one kind of thing really hard. I was like, why are we doing this so much? It really feels like not the focus of the class, but it's not up to me to decide what is taught. So anyway, all right. Questions about this before we talk about the other kind of differential equation we're able to solve? Again, these are both examples of separable differential equations because we brought all the y's to one side and all the x's to the other side, or whatever the other variable is. All one thing on one side and the other thing on everyone to their own sides. Nobody gets to play together. Everyone's playing apart. All right. But now we have this other thing. This other differential equation, dy dx equal to 3x minus 2y, which I will just remind you is not separable. So I'm going to make a very broad statement here. If something's not separable and you're able to solve it, in this class, it means it had to be first order linear differential equation. There are lots and lots and lots and lots and lots of other types of differential equations that can be solved using other different methods that you learned in the class called differential equations. But in this class, we have two methods, either separable or the thing we're about to do. So if it's not separable, you should try the other thing. And the other thing requires, first, you have to write it in the right format. So the first order linear differential equation, which we often abbreviate because it's a lot to write, FOLDE. The format has to look like this. It has to be y prime or dy dx, whichever way you want to write it, plus a function of x times y, just y, can't be anything else, is equal to another function of x. This is called a first order equation because you only have the first derivative. If there was a second derivative, we call it a second order equation. So the word order refers to how many derivatives you have taken in your differential equation. If there was a y triple prime plus y double prime equal to y, it would be a third order differential equation. The linear part refers to the fact that you have y to the first and no other powers of y. You can't have a y squared or a y cubed or a 1 over y or anything other than y to the first. So this is the general format we have to write it in to be able to use the process we're going to use. So if you have something times y prime, you got to fix that before you can do anything else. So here, I'm going to rewrite this. So I'm going to rewrite my differential equation, and I'm going to rewrite dy dx as y prime just because it's nicer. So I'm going to rewrite it as y prime plus 2 times y equal to 3x. Here, 2 is playing the role of my p of x, and 3x is playing the role of q of x. The first thing you have to do after you've written this in the, I should say the first thing, the next thing you have to do after rewriting this in the correct format is to find what we call the integrating factor. So the integrating factor, which most textbooks and people call mu, the Greek letter of x. But some people call it like I of x for integrating. But usually write it as mu of x. It's equal to e to the integral of whatever that p of x function is. So in this case, it's going to be e to the integral of 2. And the antiderivative of 2 is just 2x. So it's going to be e to the 2x. That is your integrating factor. Okay, so I'm trying to think of who does what. Some people, some teachers are okay with you jumping to the end. Some people are not. Specifically, I know Dr. Liddell is not teaching the class this quarter, but I know he's not, like, if you ever had for this class, be like, you have to show all the steps. So I'll show you the jump to the end, but then we'll talk about the why. So here's the solution. The solution to my differential equation is going to be y as a function of x is equal to 1 divided by the integrating factor times the integral of q of x times the integrating factor mu of x dx. That's, I mean, and then you have to still do the integral, but that is the solution to this differential equation. Let's find the solution, then we'll talk about actually where it all comes from, because I think it actually is pretty neat the way this always works out. Okay, so yeah, my pens are dying. I need new pens. Yeah, not really. So in this case, it's going to be 1 over e to the 2x times the integral of q of x times mu of x, which is e to the 2x. Now, don't be silly like I used to be when I did this, when I learned it the first time. I was like, oh, I can just cancel those e to the 2x's. That's not the way this works. You can't bring that e to the 2x out of the integral and cancel the other one there. Also, if we could do that, don't you think someone would have written it as just the integral of q to the x? They would have, but they didn't, because we can't do that. So here, we have to do this integration first. Oh, let's see if we get to do integration by parts. Fun times. So we're going to have our solution here. Yeah, we can, sure. Let's do it over here. So in our integral there, we should pick u equal to 3x. Our dv has to be the rest, which is e to the 2x times dx. Our du is the derivative of 3x times dx, so 3 times dx, and v, the antiderivative of e to the 2x is e to the 2x divided by 2. This is going to equal 1 over e to the 2x times the entire integral of this, which is the entire uv minus the integral of v du. So 3x times e to the 2x over 2 minus the integral of v du. So 3 times e to the 2x over 2 is 3/2 e to the 2x. And then we can just integrate that. So that's going to end up being, yeah, I can fit this in here. Sure. Sorry, it's like, I feel like I don't want to really use another page because I'd like to make it fit. So that's going to be 3/2 x e to the 2x. And then we're going to get a 3/2, and the integral of e to the 2x is another e to the 2x divided by 2. So we're going to get minus 3/4, because we're dividing by another 2, e to the 2x, plus c. And it is super important that this 1 over mu multiplies the c. It is vital that that happens, otherwise your answer is wrong. So then you could leave it like this. Personally, I would normally distribute this to each of those terms, and look what happens when we distribute that. 1 over e to the 2x times e to the 2x is 1. So I just get 3/2 x. 1 over e to the 2x times e to the 2x is 1. So I just get a 3/4. And importantly, 1 over e to the 2x times c is a constant divided by e to the 2x. So my solution is right there. That is the solution to the differential equation dy dx equals 3x minus 2y. If you really wanted to, you could verify it. You could take the derivative of that, plug it in there, take y, plug it in there, and see that the derivative is equal to 3 times x minus 2 times all that. You don't need to do that, but you could if you're curious. So, why does this work? Because like I haven't actually, you know what, we should do that, because you have no reason to believe me that this is true, other than like I'm an honest person and wouldn't lie to you. I'm trying to teach you math. But like really, I said a thing. I said that's the answer, but we have no real actual proof that it is. So let's actually go ahead and see that it's the answer. And then we'll talk about how we got there. So let's go back and say, all right, so I'm going to take y equal to 3/2 x minus 3/4 plus c divided by e to the 2x. Also, taking the derivative of this is going to be much easier than the derivative of this mess over here. So it's good to have simplified it. And I should really have written this as c times e to the negative 2x. Y prime is 3/2 minus 0 plus the derivative of c e to the negative 2x is c e to the negative 2x times negative 2. And now I'm going to plug all that into y prime equal to 3x minus 2y and hope that it works out. Actually, let's plug it into y prime plus 2y equal to 3x. So I can start with the left-hand side and make it look like the right-hand side. So let's see. Y prime plus 2y is going to be all of this. So y prime is going to be 3/2 plus, I should have said minus, oh well, too late now. C e to the negative 2x times negative 2 plus 2 times all of y, which is 3/2 x minus 3/4 plus c e to the negative 2x. All right, so let's simplify here. I've got 3/2 minus 2c e to the negative 2x. 2 times 3/2 is 3, so 3x. 2 times 3/4 is going to be a negative 3/4 is a negative 3/2. And 2 times c to the 2x is 2c e to the negative 2x. And check it out. The 3/2 and the negative 3/2 cancel. The negative 2c e to the negative 2x and the positive 2c e to the negative 2x cancel. And we're left with 3x, exactly as it should be. So we have really shown, oh yeah, y prime plus 2y does indeed equal 3x. So that really is a solution to this differential equation. Cool. So the short answer to the question, how do you solve a first order linear differential equation, is you write it in the right format. Y prime plus something times y equal to some function of x. You find your integrating factor, and then your solution is 1 over your integrating factor times the integral of your function q times your integrating factor here. There's still work to do after that, but that is the basis for the solution. Now, why does it work? Well, here's why it works. So what we're really doing here is we're taking our differential equation and I'll see. So why it works. So we're taking our differential equation, y prime plus 2y equal to 3x. And we're going to multiply the entire equation by the integrating factor. So we multiply by mu of x, which in this case was e to the 2x. Okay. I'm going to be careful about this. Yeah. So I'm going to get e to the 2x times y prime plus e to the 2x times 2 times y equal to e to the 2x times 3x. And here is what is always true, which is kind of neat, I think. This left side here is a product rule. It is the derivative of some product. All this here is the derivative with respect to x of e to the 2x times y. Let's check it out just to make sure. So if I do the product rule, it's the derivative of one thing times the other thing plus the derivative of the other thing times the first thing. So it's the derivative of y times the other thing plus y times the derivative of the other thing. And the derivative of e to the 2x is e to the 2x times 2. So literally, this is a product rule derivative here. And that always happens with this first. That's why we multiplied everything by e to the integral of p of x, is so that the left-hand side becomes this derivative of a product. Still equal to that, e to the 2x times 3x. Yeah. But then, if the derivative of e to the 2x times y is equal to all this, then we can say that e to the 2x times y is equal to the antiderivative of all that. Right? If the derivative of a function is equal to something else, then to find the actual function, you anti-differentiate to something else. But look, this is exactly what we said. If I solve for y here, I exactly have y equal to 1 divided by e to the 2x times the integral of, I'm going to rewrite that as 3x times e to the 2x dx, which is exactly what we started with, right? When we were doing the solution, we exactly said, oh yeah, our solution should be 1 over e to the 2x times the integral of 3x times e to the 2x. That's exactly what we're getting there. So this is the process for getting from your integrating factor to actually the fact that your solution y is equal to what it's equal to. Do you have to do this? Good question. I don't know. Your professor might say, yeah, I want to see all that work when you do this kind of thing on the test. Or they might say, no, you can jump straight from knowing what mu is to the answer, which is 1 over mu times the integral of q times mu. But that's not up for me to decide. That's up for you. So that's what you have to look out for. And then I should say on top of that, if your professor even covers this topic. I definitely know some of them are, because I've seen some homework problems that have it. Like I think Goldsmith is for sure covering this. I don't know about anyone else yet, because I haven't seen any assignments that either explicitly cover it or explicitly miss it. So well, let's do one more and then we can see where we're at, because there is something definitely that I want to make sure you all are aware of here. Yeah, let's not do that one. Yeah, let's do this one. Cool. So let's say we have something like, let's say we have the following differential equation. We want to solve, sure, t times y prime equal to 4y plus t to the 6th times e to the t squared. Yeah, looks terrible. Is it separable? Is always the question you should ask yourself if you're trying to solve this thing. Definitely not separable. There's no way you could break this apart. So usually if there is a y prime on one side and addition or subtraction on the other side, it's a pretty good sign it's not going to be separable. Sometimes you're able to like factor out all the one variable, so it is, but often not. So probably not separable. Even if it was separable, you still could do it this other way, but I wouldn't. So since it's not separable, we need to reformat it. So one, I want the y prime and the y on the left, and two, I want y prime by itself. So I should divide everything by t. So I have y prime. 4 divided by t is 4 divided by t, but I'm bringing it over to the other side, so it's actually going to be a minus. Minus 4 over t times y equal to t to the 6th times e to the t squared. And what I would really strongly recommend for this is to always write this as y prime plus your function of t or x times y equal to your other function of t. Because it's super duper important that if there's a minus sign there, you capture that, and that goes up in your exponent when you integrate. Right, so the format always has to be y prime plus a function of t times y equal to a function of t. So meaning the function of t has to be the negative 4 over t, not just 4 over t. All right, integrating factor, mu of t instead of x this time is e to the integral of our p of t, which is e to the integral of negative 4 over t dt. The negative 4 comes out. The integral of 1 over t is the natural log of the absolute value of t. We definitely ignore any absolute value shenanigans over here. So when I do this, I'm going to get e to the negative 4 times the natural log of t. No plus c, no absolute values. We're not worrying about that stuff at all for this. And although it's fine to have that, it is really in your best interest to simplify this as much as possible. And this definitely simplifies. If you have an e to the something with a natural log, you should rewrite this as e to the natural log of t to the negative 4th, which is then just t to the negative 4th. Should we do it the long way again? Guys, like, no. Fine. We'll do it the short way. So the short way is just, the short way I will say does require memorization, right? You have to remember what the solution is. So the short way, and I would really just think about writing the general formula first before you try to plug in the actual thing. So I would encourage you all to, if you're going to memorize it, memorize 1 over mu times the integral of mu times q. Kind of rhymes, kind of. 1 over mu, integral of mu times q. Do those cancel? Definitely not, right? If they canceled, we would have canceled them already. There's no reason to write this if they cancel. So they definitely don't cancel. I was trying to think of a time when you could cancel them, but that seems silly. So let's just not think about that. So I've got 1 over t to the negative 4th, which I should just write as t to the 4th, which I will in the next step. Integral of 1 over t to the negative 4th, not 1 over, sorry. Oof, terrible. I'm an awful human being. 1 over t to the negative 4th times the integral of t to the negative 4th times t to the 6th times e to the t squared. And that looks like it's going to be not good. Did I make a mistake somewhere? Did. Yeah. Huh. Sorry, 1 second here. Let me check one thing here. What is going on here? Yeah, that's terrible. Sorry. So I made a tiny error. Actually, the notes I'm copying made a tiny error in the beginning. This should have been a t. So let's talk about why this is an error and why it's a problem before we fix it. So if I try to write this out, what's t to the negative 4th times t to the 6th going to be? T to the 2nd. The integral of t to the 2nd times e to the t squared is not going to lend itself to a u substitution. So I let u equal t squared, the derivative is 2t, and I have a t squared here, which is kind of too much. And I can't do integration of my parts because you literally cannot anti-differentiate e to the t squared. It can't be done. Like, end of story. So the problem here is I need to fix this, really, is what really needs to happen, because that should be a fifth power, not a sixth power. So that should have been, to start off with, a t to the fifth. I apologize. Let's fix all those sixes, turn them into fives. Not too terrible. Which doesn't change anything we've done so far, right? Right, when we found mu, it's just the integral e to the integral of p of t. Oh, I'm dumb. No, I'm stupid. What did I do that I forgot? Well, from this step to this step, where this should have been a 6. Sorry, I feel bad for disparaging the person who wrote these up, because they did a perfectly good job and I missed something. From here to here, what did we do to both sides? Divide by t. Where did I forget to divide by t? Right there. T to the 6th divided by t should have given me a t to the 5th. So it's a good lesson for myself and for everyone, is that when things seem like they got to a place where something's impossible, to go back and check your work, because maybe you've missed a small thing that's going to fix the whole thing. If we go back and fix this now, where that's a t to the 5th, like it should have been the whole time after we divided all sides by t, then t to the negative 4th times t to the 5th is just t, and a u sub is going to work out great here. So I've got, let's rewrite this as t to the 4th instead of 1 over t to the negative 4th. And I got the integral of t times e to the t squared, which is much more reasonable. So for this integral over here, we're going to do a u sub. We're going to let u equal t squared. Du is going to be 2t dt. So 1/2 du is going to equal t times dt. So this is going to be the integral of e to the u. Sorry, let's figure it out. So that's going to be the integral of 1/2 e to the u du, which is going to be 1/2 e to the u. So then this is going to end up equaling t to the 4th times 1/2 e to the u, which is going to be 1/2 e to the t squared. Okay. I've written this in a way that's kind of wrong, because this t to the 4th should multiply the entire antiderivative, including the plus c. It is vital, vital, vital that whatever over as in front over here has to multiply that c there. So I like to multiply it out. I would write this as t to the 4th over 2 times e to the t squared plus c times t to the 4th. That's how I would write out my final answer. You don't have to distribute the t to the 4th, and it probably makes less sense to here than in the previous problem, where things kind of cancel out nicely. But in my mind, it's the thing you do. So that's what I would do. Question so far. You do a word problem. Yeah. There's definitely a very kind of typical word problem that people do for these kinds of things. Yeah. Yeah. Yeah, let's do that one. Cool. So, notes, don't do that. Okay, right. So many of these types of problems come up if your teacher covers this topic. So the type of problem I'm talking about is usually referred to as a tank problem. Here's the setup. The tank initially holds or contains whatever 100 gallons of a solution with 10 pounds of salt dissolved in it. And then we're going to add stuff and also remove stuff. We're going to add a solution containing 2 pounds of salt per gallon, which seems like a very salty mixture, is added to the tank at a rate of 4 gallons per minute. And then if the problem is set up in a way that's not going to suck extra, they should be removing the same amount of volume at the same rate. So I'm adding 4 gallons per minute. I'm also going to remove 4 gallons per minute. If it's a number of gallons per minute, the problem becomes even more challenging. And usually we don't do that level of difficulty in this class. So let me know if someone's doing that. We'll cover it, but I don't think we should talk about it unless we have to. And so then some important words here. The well-stirred mixture in the tank is drained at the same rate at 4 gallons per minute. So we're adding 4 gallons every minute. We're also subtracting 4 gallons every minute. So the volume in the tank is not actually changing. It's going to be 100 gallons the whole time. But the concentration of salt is going to be changing. So let's start off with, we want to write and solve a differential equation for the amount, not the concentration, the amount of salt in the tank at time t. And yeah, of course, sorry. Setting up the differential equation is actually usually not too terrible. So let's set it up. Differential equation. So when we talk about a differential equation, you're talking about having an equation with the derivative of something, aka the rate of change of something. So we're going to say, okay, well, the rate of change of salt. So ds dt, the rate of change of salt. Well, very, very kind of generally, it's going to be how much salt is going in every minute minus how much salt is going out every minute. Or the rate in minus the rate out. Great. How much salt am I adding to the tank every minute? Well, the amount of volume I'm adding per minute is 4 gallons. Let's talk about the concentration first. The solution I'm adding every so often is a solution that is 2 pounds of salt per gallon. So we have 2 pounds per gallon. That is the concentration of what's going in. And then it's going in at a rate of 4 gallons per minute. So every minute, I'm adding 8 pounds of salt. Right? 2 pounds in every gallon, 4 gallons every minute. 2 times 4 is 8. Concentration, rate that's going in. Minus, and this, now here is the part that always used to trip me up when I was doing this the first few times. Like, I don't really get why we're doing this, but eventually it made sense. So we'll skip the concentration part. The rate going out is also going to be 4 gallons per minute. That's the rate out. Or the rate of volume going out, I should say. What's the concentration of the salt in the tank? Well, in the beginning, it's 10 pounds per 100 gallons. But the problem is, it's changing, right? We're adding salt to the tank and also taking salt out. So the concentration of salt in the tank, and bear with me here, this is the part you should really hear. The concentration of salt in the tank is the amount of salt in the tank divided by the volume of the tank. That's the concentration, right? If there's 30 pounds of salt in the tank, then the concentration of salt in the tank is 30 pounds per 100 gallons. It seems very easy when you say the words. Oh yeah, it's just the amount of salt divided by the amount of volume. But it can be hard to wrap your head around that. You're putting the function right there. That is the function S that we're actually trying to solve for. And look, we have a differential equation, an equation involving a function and one or more of its derivatives. This part here is the salt that's going in. This part here is the salt that's going out. So there's a differential equation. Let's make it a little bit easier. So I just point out here, the gallons cancel. You get 8 pounds per minute. Here the gallons cancel, and you get S times 4/100. So let's rewrite this without all the units so we can make it easier to solve. So we have ds dt equal to 8 minus 4 times S over 100. Technically, this is separable. You could totally separate it. I don't love separating. I actually feel like I've definitely evolved on this position over the years. We can come back to it next class and talk about how it separates. Well, let's do it the kind of more typical way, which is using a first order linear differential equation. So let's rewrite it as, let's say this is S prime here. So I have S prime, bring this over, plus 4/100 is 1/25 times S. Try to make your S's not look like 5s. It's a real challenge for me. Equal to 8. So this is the format of a first order linear differential equation. There's our Q of T. There's our P of T. So now we're going to find the mu. Mu of t is e to the integral of p of t. That's going to be e to the integral of 1/25, which is just e to the t over 25, which is not very exciting, but this is what it is. Then our solution is going to be S of t equal to 1/mu times the integral of mu times q. Say it enough times, you won't forget it. 1/mu times the integral of mu times q. It kind of rolls off the tongue. You make a song out of it. 1/mu times the integral of mu times q. Yeah, that works. It's gonna be the new hit song. 1/mu times the integral. Yeah, I like it. I'm gonna be singing that later time. Be like, yeah, 1/mu integral. My mind was thinking, what are you talking about? Like, it's a fun math thing. So 1/e to the t over 25 times the integral of e to the t over 25 times 8. Well, that's not terrible. I know how to integrate e to the something times t. You just divide by the constant. So that's going to end up being 1/e to the t over 25 times 8e to the t over 25 divided by the coefficient of t, which is 1/25 plus c. So then if we multiply this through, 25 times 8 is 200. So you get 200. 1/e to the t over 25 times e to the t over 25 is 1. But then this times that is going to give you a c over e to the t over 25. And that is our solution. Well, that's our general solution. And then to find c, we have to use the initial condition. So this is the amount of salt at times t at time t. But then if I plug in t equal to 0, and how much salt did I have in the beginning of this problem in the tank? 10 pounds. And that's equal to 10. I should get 200 plus c over e to the 0 equal to 10. So it looks like c has to be negative 190. So my actual solution is going to be S as a function of t equal to 200 minus 190 over e to the t. It feels slightly, no, this seems fine. I feel like I'm doing something silly here, but no, that makes sense. Yeah. Interesting fact about this kind of these tank situations is, so let me ask you all, if I let time go on and on and on forever and ever and ever, e to the t over 25 gets really, really, really small or big? Just the denominator, small or big? Big. So the whole fraction gets small. So the amount of salt in the tank is getting closer and closer and closer to how many pounds? A lot, right? How many? 200. Okay, here's the point though. Right, this is going to go away. So the concentration of salt in the tank is getting closer and closer and closer to 200 pounds per 100 gallons, or 2 pounds per gallon, or the concentration of the thing we were adding. And that is always true for problems like this. If you're putting stuff in and taking stuff out at the same rate, the concentration of the tank as time goes on and on and on gets asymptotically close to the concentration of the solution that you're adding, which is kind of interesting. I think it's really neat. If you let this process go on and on and on forever, the thing you're adding in essentially dilutes the stuff down to its concentration. Cool. All right, we'll talk more about stuff next time. We can do it, and I'll just say next time, if you want to, we can solve this using separable instead of first order linear, if you care to.